Graphing the basic quadratic function q of x equals x squared is shown right here on the right. It has this shape, this kind of like a weird U, a little bit expanded, and it touches the x-axis right there at the origin 0, 0. This shape is called a parabola. And all quadratic functions have this similar shape. Sometimes it's going to be flattened down if it's transformed. Sometimes it's going to be stretched. Sometimes it's going to be moved around in the plane. But it all kind of looks like this shape. Now, for a quadratic, there's no issues with any real number being squared. So that means the domain is everything. The range, of course, if you plug in any negative number and you square it, you get a positive number. If you plug in 0 and you square it, you get 0. If you plug in any positive number and square it, you get a positive number. That's what you see here on the graph. All these things on this side is negative numbers. If you square them, you get positive numbers. This side, you get positive numbers squared, you get positive numbers. And of course, 0 is the lowest value that you square, you get 0. So 0 is the smallest value, and the function goes on up towards positive infinity. So everything between 0 and infinity are included. Now, on this graph, you can see that the left half here of this graph, as we go left to right, we're always going left to right here. You can see this function goes downward, and then it bottoms out right here at this point 0, 0. This left half is decreasing, and it's decreasing on the open interval being the interval of the domain. That's going to be all of this value from the domain. So that's going to be the interval negative infinity to 0. And likewise, you can see as we go left to right, it's still going left to right here. From this point of 0, going rightward, you can see that the function actually goes upward. And these are all positive, more and more positive values of y. Therefore, the function is increasing on the right-hand side. And this is on the open interval of the domain from 0 to infinity. We always look at intervals of the domain, not the range. Okay, this turning point, of course, is an interesting point because that's where it changes from decreasing to increasing. This turning point is the minimum of the function because that's the lowest point that it can possibly be. Now, for this function, over its entire domain, this is the smallest value it can be. So for this function specifically, this is called a global minimum. Think of like the globe being, everything, all possible values of the function, because the globe is all, the entirety of the Earth. So this minimum is the lowest value possible for the entirety of it. So that means it's a global minimum. If it weren't the global minimum, for instance, if it was like this, and this is what the function looked like, this would be called a local minimum. This one here would also be a minimum. It is a local minimum as well as a global minimum for this function that I've drawn. But a more specific term would be either local or global. All global minimums will be local minimums too. Okay, now let's consider the flipped version of this. And I've called it p of x equals negative x squared. So we know that this is, right, if we have a f bx minus c plus d, all that's changed here is that a is now negative 1, which means it's flipped vertically. And of course, the graph shows that here. The domain range is still everything, the domain is everything because there's no issue squaring a number and then taking the negative of it. So there's no issues there. And once again, if we think about the negative numbers that we plug in, negative number squared is a positive number, but then we make it negative. So negative numbers become negative. Positive numbers that are squared are positive. And then if we make it a negative, they of course become negative. So we have all these negative numbers here. And of course, 0 squared is 0, negative 0 is still 0. So the range is from negative infinity to 0, as you can see here on the graph. I was just showing you another way of thinking about it. And now, as we go left to right, you can see that this function goes upward for this first half. This is an increasing, so it's increasing on the right open interval of negative infinity up to 0. This is an increasing portion of its domain. Open interval means that there are always parentheses around it. Okay, and of course, on the left-hand side, or sorry, the right-hand side, the function goes downward as we go from 0 to infinity. This is a decreasing portion from 0 to infinity. Now, I didn't say here what this point was also called. This point is a minimum for the function. And this turning point for a quadratic function specifically, this turning point is called a vertex. So the vertex is at 0, 0 here. All quadratic functions have this parabolic behavior, and all parabolas have a vertex. So a vertex is the special point that we always kind of want to keep in mind. It's kind of like the center of a circle. The vertex centers, quote unquote, centers the quadratic function. And now you can see here, the vertex for this one is also 0, 0. And this is a global maximum, because this is the highest value the function ever reaches at this point. You can also say local maximums for ones that are, you know, like this. That would be a local maximum. This would also be a local maximum just for a small period, but it's also the global maximum for that function that I've drawn. Okay, now we're going to look at another quadratic function. You can tell it's quadratic because it's the only thing, the highest power in this is squared, and there's no other powers besides maybe 1 like that. And then if it's not written there, x to the 0 is just equal to 1, so that's how you can write no variable terms. So this is a quadratic function. Of course, if you just graph it, you're going to see it's got a parabola. And I've written it like this. But this is just, if you expand it all, it just becomes this ax squared plus bx plus c. That's the standard form of a quadratic. And that's how I've written it here in the second portion. Okay. Of course, this quadratic is increasing on the right-hand side, right? On this portion here, it's going upward. So we know that it's going to be increasing on this portion of the domain. This spot right here is the vertex, so that's where it changes. So it's increasing from what it looks like 2 to infinity, and decreasing on this portion of the domain. On this side, as you go left to right, always think about left to right here. We're going downward, so it's decreasing, then it bottoms out for a moment, and then it goes upward. So it's decreasing from negative infinity to 2. Okay, the vertex, of course, is located right here at this point. This point may not be apparent to you what it is. Of course, it's going to be an x-coordinate of 2, and this actually ends up being directly halfway, so this is 1/2. And the vertex for this quadratic is a minimum. Now, the vertex form of a quadratic is something that we need to keep in mind. The vertex is an important portion of a quadratic. It always locates the minimum or the maximum of a quadratic, and it kind of acts like a center point. You can use it to draw it in your own mind if you wanted to, or to finding it. Finding it, we always kind of want to find when we're working with any kind of quadratic in the in an application type setting. So the vertex form of quadratic is a special way of writing it. I'm going to write it like q of x for quadratic equals a times x minus h squared plus k. And the different color here, hk is the location of the vertex. The value a changes the shape, so it can either flip it, stretch it, or compress it. And this is the form that I've written here, or I've drawn here in the yellow highlighted. X minus 2 squared plus 1/2. You can see that h here is at 2 because it's x minus h, not x plus h, right? So this is just 2 here for h. And this is k. K, of course, is just 1/2. And if you look at the vertex, we have 2 1/2 right there on the graph. Since a is 1, we have not stretched or compressed this, or even flipped it, this shape. So it's going to be the standard quadratic shape. For that, you really a quadratic will always go over 1, up 1, over 1, up 1, then over 2, up 4, 1, 2, 3, 4, over 2, up 4, 1, 2, 3, 4, and it looks like this. That's the standard shape of a quadratic. You can see here if I go over 1 and I go up 1, of course this is by half, so we're going to go up by half. Over 1, up 1. Over 2, up 4. So we have 1, 2, 3, 4. Over 2, up 4. 1, 2, 3, 4. It's not really that necessary to understand the shape because you can just graph these things. But that's what the basic form is. And then anything squashed or stretched will change from this basic shape. Now, of course, this thing has a minimum, as you can see here, right? A minimum of the graph. And we know it has a minimum because a in this vertex form is positive. That means it's not been flipped. If a is negative, that means it'll flip upside down, and the minimum will then become a maximum because that it would flip. So that's how you can always tell if a quadratic has a minimum or a maximum. Now, this a is actually the same a in this standard form of a quadratic. It's the same value. So you'll actually know by looking at the standard form or the vertex form if it's a normal flipped or upward. This is actually called open up because the quadratic opens upward. Like this is the opening and it opens upward. And then if it's flipped downward, it's called open down. That's just a minor thing though. You'll know if it has a minimum or a maximum depending on what value a is. Okay, this function, of course, has a domain of -infinity to infinity. There's never any issues plugging in a number that gets squared and then, multiplied by 4 and then added on 9.5. There's no issues with any number there. So that means all the domain is that. The range, however, depends upon the vertex because the lowest value, this is a minimum, a global minimum for this function. So we know the lowest value it can ever achieve is the same as the y value of the vertex. The y value of the vertex is 1/2. So we know that the minimum for the range is 1/2. And because the quadratic always behaves the same way, it just goes upward to the left and right continuously, we know it goes up to infinity. So the vertex, not knowing if it's open up or open down, depending on if a is greater than 0 or a is less than 0, and then knowing where the vertex is, tells you the domain range. Well, the domain you already knew, the range you can find from that information. Okay, as I've said, the standard form of a quadratic equation is, let me write it like this, ax squared plus bx plus c. And we want to find, sometimes if we don't know what the vertex is, sometimes it's a little bit difficult to see on the graph because it's not a nice number. there is a way that we can change the standard form into vertex form, and we use completion of the square to do it. Now, this process is a little bit tedious. It just has a bunch of steps to it, and you just have to follow the steps. The first thing you have to make sure is that you have it in the standard form. This is not in standard form, so I want to rewrite it first. I'm going to rewrite it as x squared minus 6x plus 10. And now I can go through the process of completion of the square. So the first thing I'm going to do is I'm going to see if a is 1. Here a is 1, so if a was not 1, I would actually divide a out of both this term and this term. But since a is 1 here, I don't have to worry about that. I can continue with the process. So we have, of course, a, b, and c. b we're going to take, we're going to divide it by 2. So in this case, b is -6, divided by 2 is -3. Then we're going to take that number and square it. -3 squared equals 9. Okay, we do this because we want to add and subtract this special number right here. And then we're going to bring down the 10. And it just so happens that this is a perfect square. If we factor it, this factors down into x minus 3 squared. I recommend you expand that yourself and show that that's actually true. Try and factor it yourself and show that it's true as well. So I can plug this thing in. I can change this portion to this. So doing that, I get x minus 3 squared. And I have minus 9 plus 10. Of course, minus 9 plus 10, that's just plus 1. And this is the vertex form of this quadratic. I use completion of the square to find it. So the vertex of this, I can say real quick, is 3, 1. I know the range then, or sorry, yeah, the domain is everything, -infinity to infinity. And then the range, since this is open up, a here was 1. So we know a is 1 here as well. That means it's open upward. The vertex is a global minimum. It looks like this, right? This is located at 3, 1. So I know the range is from 1, that's the lowest value, up to infinity. Okay, why don't you give us a try in number 1? Okay, now there's actually a faster way to find the vertex, and we don't have to use completion of the square. And that is to look at this standard form and just find the x-coordinate of the vertex is always equal to this, -b over 2a. Now, I'm not going to prove that here. I will prove that later on, so that you don't have to just take my word for it. I will show you why that's the case. But this is what the x-coordinate of the vertex always equals for a quadratic equation. And the y-coordinate, well, that's quite easy to find. All you have to do is plug in this x-coordinate into the function, and you get the y-coordinate. So the y-coordinate, say y equals f of -b over 2a. So plug the x-coordinate into this function, calculate it, that's your y-coordinate. Now, a vertex also tells us what's called the axis of symmetry. Every parabola, the parabola has an axis of symmetry in it. The shape is symmetric on the left and the right-hand side across the vertex. Now, when we look at this for the standard one, it's just going to be right here on the y-axis, that we have a mirror image. If we just flip it right across this y-axis spot, we have a mirror image of it. And so that's what symmetry is here. So this axis, y equal to 0 line, this vertical, sorry, x equal to 0, this vertical line, is the axis of symmetry. For this one, you can see once again, we have the y-axis, The y-axis is our axis of symmetry. You can see, once again, we have this mirror image. It just reflects right across the y-axis. So x equal to 0 is the axis of symmetry. That's the equation of the line. That's the axis of symmetry. And for this one, this is actually the one I showed you above. This vertex was at 2, 1/2. The axis of symmetry of this one is right here, the vertical line going right through the vertex. I can mirror image it right across there. That's the axis of symmetry for this one, and that is at x equal to 2. So you can see the x coordinate of the vertex is at 0, x equal to 0. The x coordinate of the vertex here is at 0, x equal to 0. The x coordinate here at the vertex is 2, x equals 2. The axis of symmetry is always located at the x coordinate of the vertex. So we can use this information, all that we've looked at, and we can find everything right off the bat using our negative b over 2a is the x coordinate of the vertex, and the y coordinate is f of negative b over 2a. So first off, what's the vertex of this one? Well, that's quite easy to find. A is 1/4, b is -6, c is 10. So the x coordinate is negative b, b is -6, so it's going to be +6 over 2 times a. A is 1/4, 2 times 1/4 is 2/4, or 1/2. Multiplied by the reciprocal, and we get 12. So to find the y coordinate of the vertex, we just do f of 12 equals 1/4 12 squared minus 6 times 12 plus 10. 144 and 1/4 of that. Use a calculator just to speed this up. That's going to be -36 plus 10. It's going to be -26. Okay, and we already know that a equals 1/4. That means I can actually write f of x in vertex form by using a. X minus h. H is the x coordinate of the vertex, so 12. Plus k. K is the y coordinate of the vertex. So instead of plus -26, I'm just going to write -26. That is the vertex form of this quadratic. They didn't ask for that, but looks like this. Then we go, let's see, 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 26. That's about right there. It gets squashed by a factor of 4, so going over 2, it's going to go up 1. It looks something like this. It's not accurate, but something like that. And of course, you can see that the axis of symmetry is right here on the vertex. So x equal to 12 is the axis of symmetry. Okay, so we have our axis of symmetry. Our vertex is at 12, -26. And that is the answers to the question. Give it a try in number 2. Okay, without graphing, what is the domain range of this these two functions here? So we know the domain. That's always quite simple. There's no issues whenever you plug a number into the quadratic. So we know the domain is always going to be -infinity to infinity. I should do it like this. So the domain is going to be -infinity to infinity for both of them. Now the range depends upon the vertex. So let's find the vertex for m of x. We're going to do, let's see, x for m. It's going to be -b. b is -2 here. So it's going to be +2 over 2 times a. A is 1.5. 2 times 1.5 is 3. So that's the x-coordinate of the vertex for m of x. And now the y-coordinate is going to be x of xm, or sorry, m of xm, 1.5 times 2/3 squared. I'm going to write this instead of 1.5 as 3/2. Minus 2 times 2/3 plus 100. So go ahead and simplifying this. It's 4/9, 4/3. I'm going to make this as 300 over 3. Because this first one, I can reduce it down to that. That gives me 1 and 2, so 2/3 minus 4/3 plus 300/3. That's going to be negative 2/3, so 298/3. Let's see, 19. So no, that's the best we can do. So yeah, we know that the y-coordinate is at y for the vertex is going to be 298/3. So the range then, which I didn't really say have enough room here, a is positive, so we know that this is going to be open upward, or in other words, both sides go up. The end behavior of both sides go upward. So we know that this y-coordinate of the vertex is the global minimum, and everything goes upward on either side of it. For this next one, we know it's going to be flipped downward because a is negative 20. Finding the x-coordinate, well, it's just going to be negative b over 2 times a. And that simplifies down to, divide top and bottom by 8, so it's going to be 7 over 5. The negatives cancel, of course. And the y-coordinate of the vertex, all we have to do is just plug it in to n. Let's see, we get 14 over 1. This reduces by 5. So I need to write this as 14 over, let's see, adding them all up, we get 126 over 5. Once again, a is negative, so we know it's going to be a flipped parabola. That means that this value is a global maximum. So the range is going to be from negative infinity up to that value, but no higher. Of course, we know what the vertices are. This is the x-coordinate of the vertex. This is the y-coordinate. Equals 126 over 5. Okay, now let's actually graph these to show you that it's actually accurate. So let's graph this first one here. You can see I had to zoom out quite a bit. Because of this plus 100, it shifted upward a lot. And if we zoom in on this, Desmos is quite nice because all we have to do is click on it, and it actually shows us the vertex. So this vertex is at, let's see, that's going to be 2/3 for the x coordinate. And then 99.3 is going to be 99 and 1/3. That's the same thing as 298 over 3 is 99 and 0.3, which was what we found for the vertex. X did equal 2/3, and y was 298 over 3. And of course, the domain is, this is the minimum and everything upward because the end behavior is going up to the left and up to the right. So that's what I had there. So that's correct. Okay, now let's look at the next function. Here it is. Zoom in on the vertex. The vertex is at 1.4, 25.2. 7/5 is 1.4. 126 over 5. Let's just go ahead and put that in. 126 over 5 is 25.2. So we have it correctly. We know A was negative, so this is going to be the maximum value. Everything below it, that's what I've shown here. And this is a maximum value, and everything below it is in the range. Okay, give it a try in number 3. Okay, last thing here is the idea of what is a parabola and why is it important. Now, linear functions are probably the most useful because they're kind of the simplest functions. So they describe a lot of simple behaviors, and we can use them to describe a lot of different things. They're really like an average, you can think of it. Now, quadratics, because of this shape, it makes it very, very useful. This shape has what's called a focus, and it's always at this point here, A being the same A that we're working with, and it's going to be either up here if it's open upward, or if it's flipped downward, it's going to be like kind of down here, kind of close to the vertex, but it might be pushed away depending on the shape of the parabola. Now, if this were a mirror that was shaped this way, and you were to shine a light into it, so like assume that the light's coming in. Now the light doesn't come in all this direction, it actually comes in a direction, but we're just saying that if we shine the light directly into the mirror, all of the light will reflect off of the sides and go right here at the focus. They will all focus on the focus. Now, likewise, if instead we shine a light like right here at this spot, then the light will always go in every direction, and so it will always go backwards. Either it'll go forwards or it'll bounce off. But every time it bounces off the mirror, as long as the light's located at the focus, it will always bounce off so that everything is directly outside the parabola. It goes that direction, and that makes especially because these are like what car headlights do, that makes them shine brighter as a result, because you're not losing the light. It's all focused on one direction. Now, satellite dishes use this the other way. They receive very far away signals, and very far away signals, or for instance, like solar ovens, or like a mirror that reflects light to a certain thing, so that you can use like solar panels or things like that. Because they're so far away, it's pretty much like they're coming in directly into it in this kind of parallel fashion. And so like for the satellite, if you have the signal coming from some satellite and it comes in and all the signals bounce to one spot, the focus, or where they put the receiver, then you get the best signal for that dish. The same thing is true for like if you have a solar oven. If you have all the light reflecting to one spot, it'll cook faster because all the heat is focused there.